Hey folks, welcome back. In this video we're going to go over 3 worked examples to show you how to do problems involving blooming of lenses, also known as anti-reflective coatings. Now if you haven't already done so, check out my previous video covering the theory on this topic, and that way you can apply what you learned in that video to this one. So let's get started. Question 1 says, explain briefly why special coatings are applied to expensive camera lenses. Well, we can simply say that special coatings are applied to lenses so that destructive interference occurs for the reflected light, ensuring maximum light transmission through the lens. Question 2 says a camera lens has a thin film of material of refractive index 1.36 applied to its surface. The thin film is designed to give zero reflection of light of wavelength 690 nanometers. Part A says calculate the minimum thickness of film required. So writing down what we know from the question, we're trying to find the thickness d. We know the wavelength lambda is 690 nanometers, which we need to rewrite in meters as 690 times 10 to the minus 9 meters. And lastly we have refractive index n, which is 1.36 for the coating. Writing down our equation now for anti-reflective coatings or blooming of lenses, we have d equals lambda over 4n. Substituting in the numbers gives 690 times 10 to the minus 9 divided by 4 times 1.36, and putting that into your calculator should give you an answer of 1.27 times 10 to the minus 7 meters. Part B says to calculate the next lowest thickness of film required to give zero reflection of this wavelength. Well, you might remember from the theory video where we derived the equation for anti-reflective coatings that minimum thickness requires that optical path difference equals m plus a half lambda, where m equals 0. Therefore, we can say the optical path difference is equal to lambda over 2, or half a wavelength, for the minimum thickness d. And because this minimum thickness was for m equals 0, that means the next lowest thickness will occur for m equals 1. So we could write optical path difference equals 1 plus a half lambda, which equals 3 over 2 lambda. And remember the way we derived the expression for lens coating thickness was that we made this expression for optical path difference lambda over 2 equal to the other expression for optical path difference through the material, which was 2n coating times d. And that means we can do the same here. So if we were to write 2n coating d is equal to 3 over 2 lambda, or 2nd equals 3 over 2 lambda, and rearrange for d, then we end up with this expression here, d equals 3 lambda over 4n. So instead of just lambda over 4n, we've got this 3 term which has come from the 3 over 2 lambda here, instead of just the 1 over 2 lambda that we had before. And you might have already realised that this is just going to be the same as 3 times the answer to part A, because we've already calculated lambda over 4n. So if we do 3 times the minimum thickness, then that's the same as 3 times 1.27 times 10 to the minus 7, which was our answer to part A. And if you put that into your calculator, you should get an answer of 3.81 times 10 to the minus 7 meters. Lastly, question 3 says a glass lens of refractive index 1.6 is coated with a thin transparent film of refractive index 1.38. The coated lens gives zero reflection of light for a particular wavelength when the thickness of the coating is 107 nanometers. Calculate the wavelength of light that is removed by the lens coating. Well, writing down what we know from the question, we're trying to find the wavelength lambda. We know the thickness d of the coating is 107 nanometers, which we need to rewrite in meters as 107 times 10 to the minus 9 meters. We then have the refractive index of the coating n is 1.38, and writing down our equation for anti-reflective coatings or blooming of lenses, we have d equals lambda over 4n. Substituting in the numbers gives 107 times 10 to the minus 9 equals lambda over 4 times 1.38, and then cross multiplying to get lambda on its own, we can do the 107 times 10 to the minus 9 times 4 times 1.38 in your calculator, and if you do that, you should get a value for lambda of 5.9 times 10 to the minus 7 meters. In other words, 590 times 10 to the minus 9 meters, or 590 nanometers. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.